Hello everybody, welcome back to my channel. My name is Dave, and in today's video we're going to be taking a look at a technique called Weierstrass substitution, which is a technique that we might use to find the integral shown here. That is the integral of 1 over a minus the sine of x with respect to x. Of integration, which allows functions that are some combination of sine x and cosine x to be transformed into integrals of rational functions by means of the substitution t equals tan of the quantity x over 2. This technique was named for Karl Weierstrass, who also proved the intermediate value theorem. And although this is basically just a very special case of u-substitution, Spivak, in his famous text, calls this the world's sneakiest substitution. So let's go on and see how it's done. As I said in the introduction, t is equal to the tangent of x over 2. Based on this fact, we can calculate the other trigonometric ratios in terms of t. We can do this by considering a right triangle, since the tangent is defined as the length of the opposite side over the adjacent side. This means that the hypotenuse has a length of the square root of the quantity 1 plus t squared. Based on this, we can calculate the values of the sine of x over 2, which is equal to t over the square root of 1 plus t squared, and the cosine of the quantity x over 2, which we obtain by dividing the adjacent side by the length of the hypotenuse. Furthermore, by employing the double angle formula for the sine function, we can find the value of sine of x. So this gives us sine of x is equal to 2 times the sine of the quantity x over 2 times the cosine of the quantity x over 2. Plugging in the values that we just got, we find that the sine of x is equal to 2t over the quantity 1 plus t squared. Similarly, we can find the cosine of x in terms of t by using another double angle formula. In this case, the cosine of x is equal to 2 times the cosine of the quantity x over 2 squared minus 1. Plugging in the values that we obtained previously, we get 2 over 1 plus 2 squared minus 1. And rearranging this gives us 1 minus t squared over 1 plus t squared. Now that we have sine and cosine, we can find the tangent of x, which is equal to sine of x over the cosine of x, which is equal to 2t over 1 plus t squared times 1 plus t squared over 1 minus t squared. Doing this multiplication gives us 2t over 1 minus t squared. And finally, knowing that t is equal to the tangent of x over 2 allows us to back calculate to find d of x. Taking the derivative of both sides, we get dt is equal to 1/2 times the secant squared of x over 2 dx. And rearranging this gives us that dt is equal to 1 plus t squared over 2 dx. And finally, that dx is equal to 2 over the quantity 1 plus t squared dt. Having done all of this, computing this integral is simply a matter of making the following substitutions. The sine of x will be replaced by 2t over 1 plus t squared. The cosine of x would be replaced by 1 minus t squared over 1 plus t squared, and dx will be replaced by 2 over 1 plus t squared dt. Our integral, which was originally the integral of 1 over a minus sine of x with respect to x, gets these substitutions, and it becomes the integral of 1 over a minus 2t over 1 plus t squared times 2 over 1 plus t squared with respect to t. If we multiply both sides of that first fraction by 1 plus t squared, we get the integral of t squared plus 1 over at squared minus 2t plus a times 2 over 1 plus t squared, and we can cancel out the t squared plus 1. This leaves us eventually with 2 times the integral of 1 over at squared minus 2t plus a with respect to t. One way to solve this integral is to complete the square in the denominator. We will begin this by first factoring out an a from the expression a times t squared minus 2t plus a to give us a times the quantity t squared minus 2 over a times t plus 1. Completing the square by this technique gives us a over t squared minus 2 over at plus 1 over a squared minus 1 over a squared plus 1. This can be rewritten as a times the quantity t minus 1 over a squared plus the quantity 1 minus 1 over a squared. The second part of this can be rewritten as a squared minus 1 over a squared, and for the sake of brevity, I am going to make this equal to gamma squared to give us a times the quantity t minus 1 over a squared plus gamma squared. Integral has now been simplified considerably. What we have now is 2 over a times the integral of 1 over the quantity t minus 1 over a squared plus gamma squared. If we let u equal t minus 1 over a, we can simplify this even further to get 2 over a times the integral of 1 over u squared gamma squared with respect to u. This integral can readily be found in many textbooks, and carrying out this integration gives us 2 over a times 1 over gamma times the inverse tangent of u over gamma plus c. At this point, we need to back substitute for gamma, u, and t. If we do this, we can arrive at the final answer of 2 over the square root of a squared minus 1 times the inverse tangent of a times tangent of x over 2 minus 1 over the square root of a squared minus 1 plus c. If you noticed in our previous slide, our answer was only valid for values of a whose absolute value was greater than 1. So what happens if the absolute value of a is less than 1? We will try to find this in the coming slides. If you recall, the initial substitution yielded the integral of 1 over the quantity t squared minus 2a times t plus 1. By multiplying the top and the bottom of the fraction by a, we can obtain a over the quantity at squared minus 2t plus a. By means of the quadratic formula, the roots of the denominator are 2 plus or minus the square root of the quantity 4 minus 4a squared over 2a, which simplifies to 1 plus or minus the square root of the quantity 1 minus a squared over a. Thus, the fraction a over the quantity at squared minus 2t plus a has the following partial decomposition. We'll write it as m over t minus r1 plus n over t minus r2, where r1 is equal to 1 plus the square root of 1 minus a squared over a, and r2 is equal to 1 minus the square root of 1 minus a squared over a. The values of m and n can readily be found using Heaviside cover-up method. If we do this, recalling that r1 is equal to 1 plus the square root of 1 minus a squared over a, and that r2 is equal to 1 minus the square root of 1 over a squared over a, we'll find that m is equal to a over 2 times the square root of 1 minus a squared, and that n is equal to a over negative 2 times the square root of 1 minus a squared. We can then take the values for m and n and place them back into our integral. When we do this, we get 2 over a times the integral of a over 2 times the square root of 1 minus a squared times 1 over t minus r1 with respect to t minus 2 over a times the integral of a over 2 times the square root of 1 minus a squared times 1 over t minus r2 with respect to t. After doing some algebra and canceling things out, we get 1 over the square root of 1 minus a squared times the integral of 1 over t minus r1 minus the integral of 1 over t minus r2. Using the simple integration rule, we can get 1 over the square root of 1 minus a squared times the natural log of t minus r1 minus the natural log of t minus r2. We can then combine the laws to get 1 over the square root of 1 minus a squared times the natural log of the quantity t minus r1 over t minus r2. At this point, we should go and back substitute for t and r1. We recall that r1 is equal to 1 plus the square root of 1 minus a squared over a, and that r2 is equal to 1 minus the square root of 1 minus a squared over a. If we do this and we carry out a lot of algebra, we can cancel out a lot of terms, and eventually we arrive at a solution of 1 over 1 minus the square root of a squared times the natural log of a times the tangent of x over 2 minus 1 minus the square root of 1 minus a squared all over a times the tangent of x over 2 minus 1 plus the square root of 1 minus a squared. And this is for values of a which are less than 1. Still have one final case to examine, and that is if a is exactly equal to 1. In this case, the integral is simply the integral of 1 over 1 minus the sine of x with respect to x. We can carry out the same substitution that we did in the beginning of this video, and when we do the algebra, we have to solve the integral of 2 over 1 plus t squared minus 2t with respect to t. Fortunately, this turns out to be a perfect square binomial, so we can write down 2 times the integral of 1 over the quantity t minus 1 squared with respect to t. We can then carry out a simple power rule to find out the integration, and this gives us our final answer of negative 2 over the tangent of x over 2 minus 1 plus, of course, the constant of integration. And if a is equal to negative 1, the integral is very similar. We would have the integral of 1 over negative 1 minus the sine of x with respect to x. And once again, we can do some algebra to move the negative sign outside of the integral to get negative 1 times the integral of 1 over 1 plus sine of x with respect to x. Once again, this would simplify to negative 1 times the integral of 2 over the quantity t plus 1 squared with respect to t. And again, we would invoke the power rule, and the final answer would be positive 2 over the tangent of x over 2 plus 1 plus the constant of integration. So there we have it. This integral, despite looking very simple, actually has quite a complicated answer. If a squared happens to be bigger than 1, then the solution is 2 over the square root of a squared minus 1 times the inverse tangent of the quantity a times the tangent of x over 2 minus 1, all over the square root of a squared minus 1 plus c. If a squared happens to be less than 1, then the answer is 1 over the quantity, the square root of 1 minus a squared, times the natural log of a times the tangent of x over 2 minus 1 minus the square root of 1 minus a squared, all over a times the tangent of x over 2 minus 1 plus the square root of 1 minus a squared. And if a is equal to exactly 1 or negative 1, then the solution to this integral is negative 2 times a over the tangent of x over 2 minus a plus, of course, the constant of integration c. Thank you for watching this video. I hope this video was helpful for you. And if you liked my video, please give me a thumbs up and subscribe to the channel. Thank you very much.